Welcome to Spaceverse, your portal to cosmic adventures. In the silent void of deep space, planets orbit stars we can't even see with the naked eye. And yet, thanks to the James Webb Space Telescope, we're not only seeing them, we're beginning to understand them. Last week, astronomers unveiled stunning new images of distant exoplanets in the HR 8799 and 51 Eridani star systems. These snapshots mark a new era in planetary science, one where alien worlds are no longer abstract data points, but vivid, chemically complex environments we can analyze in breathtaking detail. The man at the center of these discoveries is William Balmer, a doctoral candidate at Johns Hopkins University. In an interview with Space.com, Balmer described the work as a major leap forward in our quest to unravel the mysteries of how planets form and maybe, just maybe, how life might emerge far beyond Earth. Let's break down how the James Webb Space Telescope pulled off what once seemed impossible. To truly study a distant planet, astronomers prefer what's known as direct imaging. That means isolating and capturing the planet's light directly, rather than deducing its presence through indirect methods like the wobble of a star or a dimmed flicker during transit. But here's the challenge: planets are dim and stars are bright. Trying to see a planet next to its star is like trying to spot a firefly next to a stadium spotlight from thousands of miles away. The glare from the host star drowns out the planet's light. And even when we do spot something, the details are fuzzy, hidden in the noise. This is where JWST's genius comes into play. Armed with the largest space mirror ever launched and a suite of cutting-edge infrared instruments, Webb can peer into wavelengths of light that are invisible from Earth. It can detect the faint glow of alien atmospheres, even when that glow is hidden behind the blinding shine of a star. Balmer and his team took that capability a step further, using the telescope's coronagraphs in a surprisingly unconventional way. Coronagraphs are special instruments originally developed to block the sun's light, allowing scientists to study the solar corona. On JWST, they help obscure a star's brightness so we can better see orbiting planets. But Balmer's team made an unusual choice. They used a very thin section of the coronagraph's mask, deliberately allowing more starlight to leak through. A risky move, but a calculated one. That leaked light created just enough contrast to help them isolate the planet's signal more clearly. Balmer joked, "We used the coronagraphs wrong, but in reality they used them brilliantly." What's remarkable is how JWST's stability and precision have unlocked techniques that once belonged to the realm of science fiction. In space, even the tiniest vibration or temperature shift can disrupt delicate measurements. But Webb's ultra-stable position at the second Lagrange point, 1 million miles from Earth, gives it the serenity needed to tease out planetary signals buried in starlight. It's this steadiness that let Balmer's team push boundaries, turning limitations into opportunities. Even more impressively, JWST isn't just improving our ability to see planets, it's transforming how we understand their atmospheres. With every photon of infrared light it captures, JWST lets astronomers decode chemical fingerprints imprinted in the spectrum. These fingerprints tell a story, not just what a planet is made of, but how it evolved. From the presence of water vapor to methane, ammonia, and carbon dioxide, each molecule reveals a new chapter in the planetary life cycle. These aren't just data points, they're ingredients in the recipe for planetary evolution. By analyzing them, scientists can reconstruct how a world might have formed, what it might be like today, and even whether it could someday host life. The JWST isn't merely observing exoplanets, it's giving us the tools to reverse engineer alien worlds. They didn't just spot planets, they captured them in wavelengths never seen before. Among the achievements, the first ever mid-infrared image of the HR 8799 system at 4.6 microns. That may sound technical, but it's huge. Earth's atmosphere absorbs much of the light at these wavelengths, making it nearly impossible for ground-based telescopes to observe. But JWST, orbiting far from Earth's atmosphere, has no such limitations. At 4.6 microns, the Telescope 3P pierced the veil and captured a detailed image of HR 8799's innermost planet, something ground-based observatories had tried and failed to do. Even more exciting? They accessed a wavelength at 4.3 microns, completely blocked by Earth's atmosphere. At this wavelength, none of these exoplanets had ever been observed before. Why does that matter? Because 4.3 microns is a window into carbon dioxide, a molecule that tells us a great deal about a planet's formation. Carbon dioxide and carbon monoxide exist in varying balances depending on how a planet formed and what elements it pulled in during its early development. A high presence of CO2 suggests an abundance of heavy elements: carbon, oxygen, magnesium, iron, the very stuff that built our own planet. And that's exactly what they found. The HR 8799 planets showed strong carbon dioxide signatures, suggesting these gas giants are rich in heavy elements far more so than their parent star. According to Balmer, this supports the theory of core accretion, the idea that planets begin as rocky or icy cores that grow large enough to attract thick atmospheres of hydrogen and other gases. But the discoveries didn't stop there. Something unexpected appeared when the team looked at the colors of the HR 8799 planets, variations that hadn't shown up in earlier observations using near-infrared wavelengths. In the mid-infrared, the differences were striking. One explanation? Vertical mixing, a process where gases in a planet's atmosphere rise and fall like swirling currents in an ocean. Balmer explained that, based on their temperatures, the planets should have visible methane in their upper atmospheres. But instead, methane was scarce, and carbon monoxide was everywhere. The reason? Vertical mixing was pulling warmer, carbon-rich gases from deeper in the atmosphere up to the surface, outcompeting the methane. A similar phenomenon appeared in the planet 51 Eridani b, where observations at 4.1 microns revealed non-equilibrium carbon chemistry. This planet, too, showed unexpectedly high levels of CO and CO2 in its upper atmosphere. And again, the implication was clear. The planet is metal-rich, and powerful convection is dragging heavier molecules to the top, where they block light and lower the planet's observed brightness. It's a stunning revelation. These alien worlds aren't just big balls of gas, they're dynamic, chemically diverse environments with evolving weather, heat flows, and possibly even storms we can only imagine. Sound familiar? That's because Earth does this too. Our own atmosphere is a swirling, chemically active layer where gases mix and shift, absorbing and emitting radiation. Understanding these alien planets is, in a way, like looking into a cosmic mirror, seeing how other worlds might behave under different conditions. But these discoveries also raise bigger questions. How common are metal-rich gas giants in the galaxy? What does their presence say about the formation of smaller, rocky planets like Earth in the same system? Could these giants influence the habitability of other, still hidden worlds? Balmer and his team aren't done. They've secured 23 more hours of JWST observing time to explore 4 additional planetary systems. Their goal? To piece together how gas giants evolve and how they might affect the stability and potential habitability of nearby terrestrial planets. With each new data set, they're not just mapping alien worlds. They're reconstructing the story of how solar systems form, one snapshot at a time. Thanks to the James Webb Space Telescope, the age of detailed exoplanet exploration is here. And we're only just beginning to understand what these distant worlds have to teach us. From carbon chemistry to vertical mixing, from core accretion to planetary weather patterns, every discovery brings us closer to answering one of humanity's oldest questions. Are we alone? Maybe one day we'll find life. But today, we've found clarity. If you loved exploring the universe with us, don't forget to like, subscribe, and hit the bell icon so you never miss a journey into the stars. This is Spaceverse, where science meets wonder. Thanks for watching. Keep your eyes on the cosmos.